Namaskar students. In this video, we will discuss that how we can find out the local maxima and minima of the function of two variables. You all are very much familiar with the concept of local maxima and local minima, and you have read some test for finding local maxima and local minima for the functions of one variable in your 12th standard. But now we will be discussing that how we can find out the local maxima and local minima if the function is function of two variables. So let us discuss the working rule for the same. So the first step, suppose we have the function say f and it is a function of two variables x and y. And we have to find out the points of local maxima and local minima for this function f. So first step will be, we will be finding all critical points. So first step is to find all critical points. And how we will be finding these critical points? These critical points will be evaluated with the help of first order partial derivatives, which will be del f by del x and del f by del y. So by considering first order partial derivatives as 0, we will be evaluating all the critical points. So that is, we find critical points by considering the first order partial derivative del f by del x as 0 and by considering the second partial derivative, which is with respect to y, as 0. So consider these two equations, del f by del x equal to 0 and del f by del y equal to 0. Solve these equations and obtain the all critical points. Now once we have critical point, for each critical point, we will be evaluating second order partial derivatives. So for each critical point, the points which we have obtained in the first step, for each critical point, evaluate R is second order partial derivative of f, that is del 2f del x2. We are differentiating f partially 2 times with respect to x. It can also be written as f xx. After that, we have another notation of t. This is another second order partial derivative and it is del 2f del by 2, which can also be written as f yy, and third notation we have is of s, which is del 2f del x del y. It is again second order partial derivative, which can be written as fx y. So obtain the second order partial derivatives r, t and s at all the critical points. After finding these r, t and s, evaluate rt minus s square at all critical points. And now let us make conclusion. If this rt minus s square is greater than 0 and this r is less than 0, then the point is the point of local maxima. Then the critical point which we are discussing here, we are considering here, that point will be the point of local maxima. Second case, if RT minus S square, this is greater than 0 and R is greater than 0. In this case, the point is the point of local minima. If RT minus S square, this is less than 0, and here we don't have any this condition, because if RT minus S square is less than 0, in that case the point is saddle point. The last case, if RT minus S square is equal to 0, then this test failed. So this is the working rule for finding the local maxima and local minima for the function of two variables. Now let us consider one problem. Find the extreme values. Find the extreme values of the function fxy. F is a function of x and y, and the definition of this function is xy plus a cube upon x plus a cube upon y. So this is the given function. We will be finding its critical points, and then we will be finding, we will be identifying which are the points of local maxima, local minima, and then at those points we will be finding the extreme values of given function, which is f. So let us start. So first step is here to find out the first order partial derivatives and equate them to 0. We have f, which is a function of two variables x and y, as xy plus a cube upon x plus a cube upon y. Now let us evaluate first order partial derivatives. Del f by del x. We are differentiating f partially with respect to x. So we will get here y, and the second term will become minus a cube divided by x square, and from the last term we will get 0 because we don't have x in the last term. Let us find out another first order partial derivative, that is del f by del y. We will get x. From the second term we will get 0, and from a cube upon y, after differentiating it partially with respect to y, we will get minus a cube upon y square. Let us name these as equation 1 and equation 2. Now for the critical points, we will be substituting these partial derivatives as 0. For critical points, fx is equal to 0 and fy equal to 0. That is, What is fx? Fx means first order partial derivative of f with respect to x, that is y minus a cube upon x square equal to 0. And from the second one, by considering fy as 0, we will get x minus a cube upon y square equal to 0. Let us name these equations as equation 3 and 4. Now solving these 3 and 4 equations, we will be finding the point ordered pair xy. From equation 3, we have y equal to a cube upon x square. Using y as a cube upon x square in equation 4. This is our equation 4. Let us put y as a cube upon x square in equation 4. We get what we get here, x minus a cube, and what is y? Y is a cube upon x square. So here we have y square. Y square will be a raised to power 6 x raised to power 4 equal to 0. That is x minus this equal to 0. X to 0. So this will give us x as 0 and x cube equal to a cube. That is x is equal to 0 and x is equal to a. So we are getting two values of x as 0 and x as a. Now, if x is equal to 0, then this y will not be defined because y is a cube upon x square. If we put x as 0, this y will not be defined. So we will not be considering this point x as 0. We will be considering the second value of x, which is x equal to a. For x equal to a, y just a cube upon x square, x is a. So we get point, this is our critical point. We get here only one critical point because another one for x equal to 0, the y is not defined. So we will not be considering this value of x. So we have only one critical point. Now at this critical point, we will be checking whether it is a point of local maxima, local minima, or it is a saddle point. For that, we will be evaluating second order partial derivatives. Now consider R. What is R? Second order partial derivative. And we are differentiating both times with respect to x. Del 2f, del x2. We have already del f by del x. We can see here, we have named this as equation 1. This is del f by del x. So for finding R, let us differentiate equation 1 further partially with respect to x. So first term is y, that will give you 0. And from the second term, what we will get from minus a cube upon x square, we will be getting here minus sign will become positive. It will be 2 a cube upon x cube. Now t is fyy, which is del 2f, del y2, and it will be, we can find out it from equation 2. It will come as 2a cube upon y cube. Now the next notation we have is of s, which is fxy, which is del 2f del x del y. So how it will be evaluated? It means del by del x of del f by del y. So we'll be differentiating equation 2. Equation 2 has del f by del y. This is equation 2. So for finding t, we will be differentiating equation 2 partially with respect to x. So what we will get? We will get 1. So it will be 1. Now we have RT and S. So let us evaluate RT and S at the point which is ordered pair AA. R at the point which is ordered pair AA, it will be 2a cube upon x cube. What is x? X is a. It will reduce to a. Then let us evaluate t at this point. What is t? Let us see here. T is 2a cube upon pi cube. When we will be considering the point, at the point y is a. So again we will get t as 2a cube upon a cube. Again we will get t as 2. And when we talk about s at this point, s is already, it's a constant 1. So it will remain same 1. We have RT minus s square equal to, let us find out RT minus s square. R is 2, T is 2, S is 1. So what we are getting? 3. Here RT minus s square is greater than 0. RT minus s square is 3, so it is positive, it is greater than 0. Now let us check the sign of R, and R, which is equal to 2, is greater than 0. So if we see our working rule, what we have discussed, that if RT minus s square is greater than 0 and R is greater than 0, then that point is the point of minima. So what we will get here, this means the point is ordered pair A is point of local minima. We have to find out the extreme values. Now, extreme value of f at this point is given by f of a comma a, and it will be xy. Let us put in the definition of the function, and the first term is xy, so it will be a into a. Second term is a cube upon x. A cube upon x. What is x? X is a. And the third term in the definition of the function is a cube upon y. A cube upon y. What is y? Y is again a. So this will be 3a square. So the extreme value of the given function is 3a square, and it is corresponding to the point a comma a, and this a comma a is the point of local minima. Let us consider one more problem. We will not be doing it completely. I will be just giving you a hint at how you can proceed for this problem. The question is, a rectangular box a rectangular box, means it will be like cuboid, open at the top, open at the top, is to have a volume, is to have a volume of 32 centimeter cube. So what is given? The volume of this rectangular box, which is open at the top, is given, and this volume is 32 centimeter cube. Find the dimensions. Find the dimensions of the box requiring least material for its construction. So this is our question. We have a rectangular box, means we have a box which is in the shape of cuboid, and we have a condition here that it is open at the top. We have base, but it is open at the top, it is not closed. And its volume is given, and its volume is 32 centimeter cube. So this is a fixed thing which is given, that you all know that the volume of a rectangular box which is in the shape of cuboid is length, breadth, height, and this is given as 32. We have to find the dimensions. What we mean by the dimensions means we have to find out L, B, breadth, and height, which is H. So we have to find out these dimensions of this rectangular box. What is the condition here? Requiring, this is the word here, least. Requiring least material for its construction. Now, what is the condition here? That the material which is used in the construction of this rectangular box is least. Now, the material required for its construction, it depends on the surface area of this rectangular box. So what we have to do, we have to minimize the surface area, and corresponding to that minimum surface area, we will be having some dimensions. So we have to find out those dimensions of this rectangular box. We have already done such type of problems based on the concept of maxima and minima, but we have done these for the functions of one variable. Because here we have to minimize surface area. And if I talk about the surface area, then the surface area is a function of three variables here, which are length, breadth, and height. So first of all, if I write down the expression for the surface area, what is the expression for surface area? If I denote the surface area by S, I am giving you just hint. You will be doing it. You can do it on your own. Surface area, since the box is open, so from the base it will be LB, and since it is open at the top, we will be considering LB only once. And for the other faces of this rectangular box, what we will be having? 2 times LH plus BH. In case box is closed, then it will be 2 times LB plus BH plus LH. So this is our surface area, or you can say this is our function, and it's the function of three variables. And we have to, what we have to do, we have to, least means minimum. We have to minimize this function. Now, there is one more thing which is given on our problem, which we have already written here, that the volume is fixed and the volume is 32. We have V, which is LBH, as 32 centimeter cube. So from here we can find out height, and this height will be 32 upon LB. And we can put this height in this expression which we have for surface area S. And once we will be doing this using this H as 32 upon LB in S, we have S, first term will be as it is because it doesn't contain H, LB, and in the rest two terms H is common. So let us take this H outside, it will be 2H, and when we will put this H, it will become 64 LB because we have 2 here. So 64 upon LB, and we will be left with L plus B. Now we have S as function of two variables. Now with the working rule which we have discussed right now, we will be finding the points of local minima. And with that value of L and V, we can find out H because H is related to LB by this relation that H is equal to 32 upon LB. So what we have to do, this S, find out its critical points by considering first order partial derivatives and equating them to 0. Then at those critical point, obtain RT minus S square. After doing this, we will be having some conclusion regarding the values of length and breadth. And once we have length and breadth, we can easily find out H. And this will give you the dimensions of the box. So in this way, you can proceed it. So with this S, apply the working rule for finding the local maxima and local minima and find out the values of length and breadth. So you can do this problem on your own. So in this way, we can do the problems in which we have to find out the local maxima and the local minima of the function of two variables. Thank you. Have a nice day.